Yep. When are AP tests? 2 weeks? You should have been practicing the test this whole time, right? So you should know what you're getting into. Oh, those are the worst. Yeah. We had, when I was in high school, we had 2 semesters and all of our AP classes were all in the spring, but we also started in January. So, and we were done in like late May. So we had most of the class already.
No, it's not. Why would you put it?
So far, this is what's written in the problem here, right? So if that's the case, what is the other product? Potassium nitrate. What's its phase going to be? Solid, liquid, gas, aqueous. Think about what happened here. We mixed 2 ionic solutions and one of the combinations turned to a solid. So the rest of them are still aqueous. Aqueous, aqueous, take your pick. Latin's a dead language. Is it balanced?
No.
2 nitrates here, only 1 there. Double it. We good? There we go. So a tip when it comes to balancing reactions with polyatomic ions, unless your polyatomic ion is changing into something else, unless we had something else with nitrate over here or with nitrogen over here, we can just treat the nitrate like it's one object. We don't have to balance nitrogens and oxygens separately, right? Because all of our nitrogens and oxygens are only present as nitrate, so nothing about it is changing between the two. It's a complexation reaction, right? It's non-redox. So all this, we should see all the same pieces before and after. They might look a little bit different, but that speeds things up. We can just count nitrates instead of counting oxygens. Then we have 25 milliliters. Of 1.20 molar KCl is added to 15 milliliters at 0.9 molar. What's the next step? Everything into moles, right? I'm very optimistic that all of the groaning when I said we were going to be doing a stoichiometry practice problem is because these are super easy for y'all now, right? Not because they feel like you're lost the whole time. It should be repetitive at this point. But you know what they say, you don't practice till you get it right. You practice until you can't get it wrong. I'll just keep saying that until we stop getting things wrong too, right? So if we're going to put these into moles, they're both solutions with concentrations. How do we do that? Zach? So capital M is moles per liter, right? So if we take our milliliters, put it in liters, then we can use moles per liter as a conversion. So 25 milliliters, and you can combine this step because if we wrote it all the way out, it'd be 1,000 milliliters is 1 liter. And then 1 liter is 1.20 moles. Since these two things are the same, 1,000 milliliters equals 1 liter and 1 liter equals 1.2 moles. We can combine those into one conversion factor if you like. If you're not sure about that, just leave it like this. It's more writing, takes up more space, but it's kind of foolproof, right? We know how to do this. So we'll get 0.025 times 1.2. How many sig figs are we going to keep? 3. 3 sig figs, infinite sig figs, 3 sig figs. Do the same thing with the other one, except it's 15 milliliters. 1,000 milliliters is 0.900 moles. Sort of, I mean about combining these two conversion factors. Something 0.045. $135. This is enough to figure out what's going to run out first.
No.
If you're good at mental arithmetic, maybe, but if not, we can show our work here. So we have 0.0300 moles here. 0.0135 moles. We're using the KCl up twice as fast, and we have more than twice as much. Right? If this was 0.015, we'd use them up at the exact same time, right? We have less than that, so this is going to run out first. And again, if you can't see that math in your head, that's totally fine. Go to our normal way of showing limiting reactant. .135 moles of barium nitrate for every 1 mole barium nitrate. Is 1 mole of barium chloride. Right, we can pick either of these to figure out what's going to run out, what our theoretical yield is. But since the question specifically talking about, well, why would it make sense to talk about barium chloride as the yield rather than potassium nitrate? Think about the logic of trying to measure the yield here. Is it easier to measure concentration of product, or is it easier to measure how much a solid weighs? So if we make one of our products is going to be solid and the other one's still dissolved, it's usually easier to get the yield by looking at what's solid. Especially considering number 4 here. It gives you a measured amount of barium chloride. That's your clue that you're supposed to be looking at theoretical yield of barium chloride. Obviously on a test, I'd try to be more specific here. I was just sloppy writing that question. One-to-one ratio. So we get 0.0135 moles product. Do the same thing with our other reactant. This one's a 2-to-1 ratio. 2 moles KCl. It's 1 mole of product. 0.015 moles barium chloride. They can't both be true, right? So we know what the real theoretical yield is and what the limiting reactant is. There's our limiting reactant. Here's our theoretical yield. All right, there's 1, 2, and 3 done. We want the percent yield. We can't actually directly measure how many moles we get of the product because we measure things in terms of grams, right? So we either have to take the 2.45 grams and turn it into moles, or we have to take our 0.0135 moles and turn it into grams. Either way, we're looking for what we actually get divided by our theoretical yield times 100. So barium chloride, fairly large molecular or atomic weight, 137. So around 207 is going to be our molecular weight. One mole barium chloride is maybe 208 with sig figs. Yeah, 208 grams.
Sorry, who? Yeah, who are you from? I don't have. Okay.
So we get something around double that. That's maybe 0.027 times 100, 2.7. Somebody say it louder. I can't. My ears are no good anymore. 2.82. That's our theoretical yield in grams. I know this is all review, but is it really seeming like it's making sense now? Like you could do this on your own, right? Ideally. If not, you should be getting closer to it at least. So the percent yield's then going to be 2.45 grams divided by 2.82 grams times 100. Something around 80%. So. Right, so next week's lab, you're actually going to do a precipitation reaction. You're going to do this in lab. Mix some solutions together, get a solid, filter out the solid, weigh it, and get a percent yield. Would it be reasonable to get a percent yield that's greater than 100? We know that we can't get a percent yield over 100 if we're actually only measuring product. But somebody who said yes, why is it reasonable to actually get a measured number over 100% yield? Impurities, oxygen in the atmosphere reacting with it. DM? Probably not, but could be. That's mostly when we get numbers like that, that's usually when we start getting into some of these exponential functions because it's really easy to be off by a little bit. And then when you raise it to the 10th power, you get a really big error. It certainly can be though, because think about what I just described. You mix two solutions together, you filter out the solid, then you weigh the solid. What else is mixed in with the solid when you weigh it? You're probably still going to have some leftover water, right? Unless you take it, and if we were really trying to get really good numbers, we would take it and we'd put it in an oven or let it sit for a week and let it dry out in our low humidity up here. If you don't do that though, basically you're going to have a whole bunch of water mixed in with your product, which means your measured number is going to be too high. And it could really easily get over 100. Physics, who's in physics here? We have a couple, right? Nobody in physics yet? Okay. Oh, it's fourth period. Yeah, same time. Physics students get really bothered when we get numbers that are way off from right at 100% error, or 100% yield. Because in physics experiments, it's really normal to only have like a 2% error, things like that. Chemistry, that's not the case. We deal with a lot more variables. And so it's pretty common to have, have your percent yield be 120% or have a 15% error. That's still a pretty good error in some cases. In fact, some of my OChem class synthesis, they're lucky if we get 20% yield, because some reactions just don't go 100% to completion. Some reactions stop after a certain amount of time. We'll talk about equilibrium in a week or two, but basically sometimes the best you can do, even if everything goes perfectly, is 20% yield. Sometimes it's less than that. If it's less than that, we don't typically do that experiment in lab. But turns out when you have lots and lots of variables, there's lots and lots of things to go wrong. And there's lots and lots of ways your percent error can be pretty off from what you're expecting. All right. Let's talk a little bit more about solubility and solutions. Because I mentioned this before when we were talking about precipitation reactions in the first place, about how if we actually have an aqueous solution of an ionic compound, do we actually have KCl floating around stuck together? Now, really, if it dissolves in water, it's because the water is actually holding the ions apart from each other. That's actually what the physical process of solvation looks like. So if we are mixing these together, we actually have this splitting into an ionic form. So this form of writing a precipitation reaction is called the molecular equation, the molecular form. But you can also have what's called the total ionic equation, which is basically anything that's dissolved, you write as separate ions. So it's more writing, takes up more space, but it's actually a better idea of what's really going on. You really have two potassiums, aqueous, plus two chlorides, aqueous, plus barium, aqueous, plus nitrate, two nitrates, aqueous. When we first mix these together, when they're in their separate containers, this is actually what we have. A whole bunch of water molecules and then all these individual ions floating around. Then when we mix them together, all of our ionic compounds, all the possible ionic compounds we can make come from taking a positive charge and adding it to a negative charge, right? So one of the first things we learned about compounds is ionic compounds, you make the charges add up to 0. You have to have a positive mixed with a negative to add up to 0, right? So we started with potassium chloride and barium nitrate. For precipitation reactions, all you do is you look at the opposite combination, which is why these reactions sometimes get called double replacement reactions. So all you're doing literally is just swap the two cations. And then make the charges add up to 0 again if they don't match already. So our other possible combination is barium plus chloride. And what this is telling us is that barium chloride turns into a solid, which means after we mix these things together, we actually do get an ionic compound forming as a solid. And then the other pieces, though, are still just floating around. So still 2 potassiums aqueous plus 2 nitrates aqueous. So really the total ionic form is just this blown up into pieces. Take everything, pull it apart unless it forms a solid. It seems like a lot of extra writing though, right? There's another form of the ionic equation or the ionic reaction called the net ionic. The net ionic form of a reaction would look like, well, what? Like a net? Good question. Would we take apart the polyatomic? Is the polyatomic actually coming apart? This was going to be where I went next after the rest of this example. Anything with covalent bonds really does stick together. They call them molecular compounds because even when they're dissolved in something else, they stick together. Those covalent bonds still hold. So, since a polyatomic ion is just a covalent compound with a net charge, it stays as a covalent compound. So nitrate stays as nitrate even when it's dissolved. So, and I'll say that again, I'll give you another example of that in a second. The net ionic equation, think in terms of economics. Or if this is our total ionic or a gross ionic, net means you cancel out everything that is a change that isn't really changing, right? So net ionic, basically you leave off anything that doesn't react, which is going to look like anything that looks the same on both the reactants and the products. So what's not changing? Potassium's not changing. 2 potassium aqueous, 2 potassium aqueous. And the nitrates. And so our net ionic, you basically cancel out anything that's the same as both the reactant and a product. So our net ionic then is just barium aqueous plus 2 chlorides aqueous makes barium chloride solid. All right, these other ions that we canceled out, the ions that don't really do anything, they have to be in there to begin with because you can't make a chloride solution without having something to balance the charge of the chloride in the first place. There's no way for you to just add chloride to a solution on its own. It always has to be in the form of potassium chloride or sodium chloride or something chloride. But that doesn't mean that the potassium is actually an active part of the reaction. So anything that's just there to balance the charge, anything that doesn't change and that we cross off here, we call them spectator ions. Kind of makes sense. They're not part of the competition. They're just there to watch, I guess. Spectator, like a sport. So one of the ways that I'm going to be testing you on this is, okay, it's kind of just like what we did here. I'll describe something in in English, written out as a sentence. And say, write the molecular equation, the total ionic and the net ionic equation for this reaction. And it's start with the molecular equation because that's the way it's going to be written. Then you take it and you blow it up. And then you take the blown up version and you cancel out anything that doesn't change. Again, a lot of writing, obviously. But conceptually, I think that it's not too tricky. I mean, if we're being realistic, once we got past quantum, none of the concepts in this class are that tricky. It's just trying to remember all of them at the same time, right? I get that. Which is why it's it can be very boring to sit through a chemistry lecture sometime because all the individual steps are simple. It's putting them all together, right? All right. Is there anything? Oh, so another example of a covalent compound. Anything that's all non-metals is a covalent compound or molecular compound. What's an example of a covalent or molecular compound that dissolves in water that you see in everyday life?
Yeah.
CO2. Sodium bicarbonate is a polyatomic ion, but also a ionic compound. Salt, that's ionic. What was the first CO2? Somebody said CO2. We talked about CO2 dissolving in water the other day, right? But I was assuming somebody might say sugar. Sugar is another good example. Depends what kind of sugar you're talking about. Table sugar is sucrose, which is, see if I can, C12H22O11. You take table sugar, you dissolve it in water. You get C12H22O11 aqueous. But because those are all covalent bonds, they all stay stuck together. And actually it works even a little bit better if we go with a smaller organic I guess CO2 works. When you dissolve CO2 in water, you still have all the same bonds before. When it's a gas, it looks like this floating around. When it's dissolved in water, it looks like this, except with a whole bunch of water molecules around it. But you're not going to pull this whole thing apart. The covalent bond, if you break the covalent bonds in a molecular compound, you wind up with a bunch of incomplete valences. With the ionic bonds, when you break them apart, yeah, you've got ions, but at least you still have everything with complete valences. Because covalent bonds form when there's not enough electrons to go around, breaking them apart would mean that you're not able to fill all those valences anymore. And that doesn't really happen. We do in certain cases. So the whole idea of solubility and things dissolving in water works better if we talk about it in terms about polarity. So polarity is basically what you get when you combine Vesper geometries with electronegativity. Right, and so I've been going back and forth about what order to do this material in, but it makes a lot of sense to do polarity now since we're talking about what these things look like. So when you have a polar molecule, a polar bond is what you get basically when you have a difference in electronegativity. So if we look at the Lewis dot structure for water, it's going to look like this, right? And if we draw out the Vesper geometry, it's going to be a tetrahedral electron geometry. It's going to look bent, right? Get something that looks like this. So that's all well and good. And we satisfied all our criteria for a Lewis dot structure. Everything's got a full valence, everything's formal charge is 0. We use the right number of electrons. Except that we don't really share the electrons equally. I mentioned that we were going to come talk about electronegativity when it came to this. What is electronegativity? Who remembers? No. So everything's paired up so far. So how strong? Bingo. Different elements pull the electrons in tighter to themselves, right? That's why we had the periodic trend of atomic radius, where when you went from left to right in the same row, things got smaller because everything got pulled in tighter by more protons, right? Electronegativity is the tendency of these atoms to pull electrons towards themselves. In other words, they're not all equally strong at filling their own valences. None of this really is a surprise. We've kind of been talking about some of these concepts for a while. But when you apply that to bonds, like the bond between a hydrogen and an oxygen, if oxygen is better at pulling electrons towards itself, it's kind of like playing tug of war with the electrons. The electrons want to be, are attracted to both the hydrogen and the oxygen, but if the oxygen's stronger, it winds up pulling more of the electrons towards itself. If you've ever had to share a hotel bed with a sibling, you know that covers are not shared evenly, right? Somebody's the blanket hog and somebody winds up cold in the middle of the night. Electronegativity is basically who's the blanket hog. More electronegative means they pull the electrons towards themselves. They cover themselves up with the electrons more, which means hydrogen is left out in the cold. So that means even though this entire molecule is neutral, even though formal charge is 0 for everything, there is an overall difference in charge because the oxygen gets more of the electrons than the hydrogen does. If the oxygen gets more electrons than the hydrogen, we get a partial charge. We don't say it's a full -1 charge on the oxygen, but it's got like, a quarter of a charge. You can't have a quarter of an electron, just like you can't, but if you go back to the sharing blankets analogy, you can have a quarter of a blanket, right? Even though you have an integer number of blankets, you personally only have a quarter of a blanket, right? And so the way we say that, we don't try to put a number to what the negative charge is usually. We just say it's a partial negative charge, and we say that with a lowercase delta. As we say, this part of the molecule has a partial negative. And since the overall charge has to add up to 0, what does that tell us about the other side of the molecule? Has to be a partial positive. Right, so in order to have, so if you have the right criteria, you get a net difference in charge from one side of the molecule to the other. If that's the case, we say that it's a polar molecule. The physics way of saying it is that it's a dipole. Dipole, two pole like a magnetic pole, like on a magnet, there's a positive side and a negative side, just like the Earth's magnetic field. A dipole means that there's a plus and a minus. All right, so the criteria for finding whether or not a molecule is going to be polar, you really only need 2 things. Depends on some other things like being able to draw out the Lewis dot structure. But basically, if it's a polar molecule, or in order for a molecule to be polar, you need to have polar bonds. Meaning you need to have a difference in electronegativity between 2 atoms. So we're not comparing the electronegativity of the hydrogen to the hydrogen because the two hydrogens aren't bound together. We're looking at the difference in electronegativity between the oxygen and the hydrogen, which you may have noticed on the periodic table that you had for the midterm. It has electronegativity values on it. This is why. Because to determine whether a molecule is polar, we basically need to be able to put a number to what constitutes a polar bond. So for it to be a polar bond, we say that the difference in electronegativity has to be greater than 0.4, which is somewhat of an arbitrary cutoff. Because even if there's any difference in electronegativity between the two atoms, which basically anytime you have two atoms that aren't the same attached to each other, you're going to have some small amount of polar character to that bond. We kind of arbitrarily say 0.4 because the difference in electronegativity between hydrogen and carbon is about 0.4. It's just under 0.4. So basically anything that's a bigger difference in electronegativity from carbon to hydrogen is a polar bond. Why do we use that as a cutoff? Well, because carbons and hydrogens tend to be kind of important to us as living creatures that are made primarily of carbon and hydrogen. And because the most common non-polar molecules that we deal with are hydrocarbons, all carbons and hydrogen. And we kind of define them as non-polar because they don't dissolve in water. Asen?
Well, that 0.4 is like anything that's 5 atoms apart.
So we're specifically talking about, there's the other way to remember it is if you don't have a list of numbers sitting in front of you, is the big four when it comes to electronegativity are nitrogen, oxygen, fluorine, and chlorine. Anything that's not one of those four, bound to anything that's one of those four, is going to be polar, with a couple of exceptions. I think sulfur to nitrogen are pretty close to the same, or sulfur to chlorine are pretty close. Might not quite hit that range, but that's a general test. Is if you see nitrogen to hydrogen, definite polar bond. You see oxygen to pretty much anything that's not fluorine is a polar bond. DM?
Still saw some sort of like positive and negative side. Could you see like a negative side bonding to a negative side of a different molecule?
Would the negative side want to bond to the negative side of another molecule? They basically don't repel each other if you get less than 0.4. But just like with lots of things in science, we kind of tend to categorize things in a binary state. It either is non-polar or polar, but it's a spectrum. Right? So this is just our arbitrary cutoff. And there is an arbitrary cutoff above that too. If the difference in electronegativity is greater than 1.8 or 2, then it's actually an ionic bond at that point. Because there's actually measured electronegativity values, say for iron. So we could look at iron being bound to chlorine and we could look at the difference in electronegativity, but it's going to be like 3 point something. If your difference in electronegativity is anything bigger than 1.8 or 2, then it's not a covalent bond at all. It's an ionic bond. So a polar bond is sort of a sweet spot between where electrons are not shared evenly, but they're still shared. And because different textbooks have different values for that upper end, I won't get too picky about that. We're just gonna stick with if it's a metal to a non-metal, call it ionic. Because almost all metal to non-metal bonds are ionic. Technically, you can make covalent bonds between carbon and magnesium, for instance, carbon to aluminum. But that's a pretty rare case given our planet. All right, so any more questions about this first criterion? There's the other criterion, though, is a little bit weird you can have polar bonds, it turns out, and not have a polar molecule. Think about, let's say we put 3 siblings into a hotel bed to share a blanket, and you put the 2 blanket hogs on the outside. That person in the middle is still going to be covered the whole time, even though they're normally the weak one that doesn't get the blankets, right? Because your 2 blanket hogs are going to be fighting back and forth the whole time, right? So you also need asymmetry. Our second criterion is asymmetry, because otherwise, if you wind up, the classic example is carbon dioxide. Carbon to oxygen is a polar bond, and carbon to oxygen is a polar bond. But because both oxygens, even though they're both bullies, they're both equally strong and pulling in opposite directions. To go back to a tug of war analogy, oxygen's an NFL team, carbon's a Pee Wee football team. If you put 2 NFL teams playing tug of war with a rope and you put a Pee Wee football team holding on to the middle, Pee Wee football team is just dragged along for the ride, right? You really still wind up with a stalemate if your 2 NFL teams are equally strong, though. So basically, you need to be able to draw the Lewis dot structure because you need to know if you have polar bonds, but you also need to know if you have asymmetry. A polar molecule needs both of these. If you can't say yes to both of these questions, then it's a non-polar molecule.
In the case for carbon dioxide, with the polar within that, like, would it just be 0? Would it not be polar at all?
Yeah,
Is it just
exactly.
okay?
And we can actually see this. Polar molecules have higher boiling points and melting points, because what happens with these partial positives and partial negatives, if we have a whole bunch of these water molecules together, every partial positive is going to line itself up so it's kind of aligned with a partial negative, right? Because positives are attracted to negatives. So you actually wind up with a case where you get these weaker bonds where every hydrogen lines up with an oxygen and every oxygen lines up with more hydrogens. So those attractive forces are what cause different phases beyond just gases. If there weren't attractive forces between the molecules, nothing would exist as a solid or a liquid. Things only exist as solids and liquids because these molecules literally stick together like magnets. Just really, really, really tiny, weak magnets. Which is why you actually get, that's actually what causes surface tension. Everybody's seen a demonstration in some science class somewhere where somebody fills up a glass of water above the brim and it doesn't spill, right? That's because those water molecules are holding each other in, are holding on to each other with these attractive forces. So to go back to the original question that DM asked about what's really happening when we try to dissolve these things, if you put an ionic compound in water, basically what you're doing is you're pulling apart the water molecules and you're sticking one of your ions in the middle. And so what winds up happening, the reason that this works sometimes but not all the time, because if you put a sodium ion, say, sitting in water, it's really going to form like this sort of octahedral shape where it's surrounded by 6 water molecules that all have their oxygens pointed towards the sodium. They're not true covalent bonds, but because we're replacing one ionic bond, a sodium ion to a chloride, with 6 bonds that are almost as strong, this is actually more stable than leaving it dissolved as sodium or leaving it as a solid with sodium chloride. And then the chloride's going to do something similar, right? Except it's going to have all of the hydrogens are going to be pointed towards the chloride. So what winds up actually happening, I'm going to leave this here for now. So we're going to come back to asymmetry in a second. This is why when you dissolve ionic compounds, they split up into these chunks like this. But when you dissolve covalent compounds, they don't. Because covalent compounds will dissolve in water if they can make the same type of interactions that the water molecules make with each other. And they don't break apart to do it. So for instance, we have another polar molecule, like say methanol is a good example. Lewis dot structure for methanol. Looks like this. That kind of looks like a water, doesn't it? A water with this extra CH3 attached to it. If you put methanol in water, it can make the same type of interactions with the other water molecules, where the methanol's hydrogen can form a weaker interaction with a water molecule. So basically, you can mix together covalent compounds with water and they don't break apart into ions because they have other intermolecular forces as long as it's another polar molecule. If we replace this with, say, we'll just use ethane. Ethane's the same size as methanol, roughly. So it's going to take up just as much space in between the water molecules, but there's no polar bonds here. Everything's just carbon and hydrogen. If there's no polar bonds, this can't make the same type of interactions with water. And it just won't dissolve. Anybody ever made like dipping sauce for garlic bread out of olive oil and balsamic vinegar? You get 2 layers, right? Because the oil is non-polar and the vinegar is polar. And you can't make favorable interactions between the two. A non-polar molecule doesn't like to mix with a polar molecule usually, unless we add some other things to the system. And so polarity winds up playing an important role, and it also kind of explains precipitation reactions. In order for something to dissolve in water, you have to be able to make similar bonds. And when the ionic forces get too big, the water molecules are not able to hold the ions apart. So in our first example, barium 2+ plus chloride, barium can be floating around surrounded by water molecules, chloride's floating around surrounded by water molecules. But when you mix them together, when they bump into each other, they stick in a way that's too tight for water molecules to pull them apart. Think about a refrigerator magnet that's so strong that you can't use your fingers to pull it off of the refrigerator. It is now part of the refrigerator until you get it like a wrench or something, right? That's effectively what a precipitation reaction is. When you make a combination of ions that sticks together too well for water to pull apart.
How would you pull them apart?
In the chemical sense, or in the chemical sense, basically you make it so that your forces between, there's a couple ways to do it, but you make it so that the forces between your solvent and the solid are stronger than they would other be. It can be making things more acidic. It can be increasing the temperature. There are a couple different tactics. Like for instance, there are certain minerals that you can't dissolve in anything short of what's called aqua regia, which is basically a mixture of 2 concentrated strong acids. If you take pure sulfuric acid and pure hydrochloric acid in a 2-to-1 ratio, you can dissolve things that won't dissolve in anything else. because it's really, really nasty. But when we use water as sort of our baseline for this, we're talking about solubility because we live on a planet where water is the most common liquid. If we were on Titan, where we were dealing with ammonia, we'd talk about how soluble things are in terms of does ammonia separate them. And so what that turns into is let's define a few other terms since we're here. When you dissolve an ionic compound in water, when you get those free ions floating around, the other term that gets used instead of just saying ions, is they're called electrolytes. An electrolyte just means that you have ions floating around in a solution. And the reason they call them that is because they conduct electricity. If you have pure DI water, it actually won't conduct electricity. We think about water as being conductive, right? That's only water that has ions dissolved in it. So that winds up being really important in biochemistry for health reasons, because everybody's heard about electrolytes, right? It's what plants crave. You haven't seen Idiocracy, you need to. I think it's streaming on Amazon right now. Brondo's got Planets Crave. What happens to people that exercise and deplete all of their electrolytes in their body through sweating? It's basically the ratio of potassium ions to sodium ions in your nervous system is what allows your brain to communicate with your muscles. If you throw off that ratio too much, then you actually wind up with your brainstem basically unable to communicate with your muscles, and you wind up with muscle convulsions, what's called ataxia, which basically kind of means clumsiness. Have you ever seen videos of people trying to finish an Ironman triathlon, and they're like, they get to the finish line and they're just like rubber legged, wandering all over the place like they're drunk? It's literally because they've run out of electrolytes in their body. And they get to the point where they can't communicate with their muscles anymore, even though they trained to the point where their muscles still have the strength. If you don't have enough electrolytes, then it doesn't matter how strong your muscles are because you can't communicate with them. In fact, that's actually one method of euthanizing animals, is you just give them an overdose of potassium ions, because it effectively just stops their brain from communicating with their lungs and their heart. And actually for a while, back in the 90s, I'm going to pick on Chico State because they were in the news a lot in California when I was growing up for having a drinking problem, especially the Greek organizations at Chico State. So they basically said, okay, Greek organizations, fraternities and sororities, you're not allowed to have any drinking at events anymore. And so instead of just, not hazing their new recruits, they just switched to hazing their new recruits by forcing them to drink water instead of, whiskey. And they still had people dying, because it turns out if you drink too much water too fast, you can do that to yourself. You basically throw off your electrolyte balance and you can go into a coma. So it turns out electrolytes are a real thing. They're not just a marketing term. They're mostly used as a marketing term now. But it's a real issue.
So that thing with the water,
Mhm.
about having too many electrolytes, would it be like way easier to do that with Gatorade?
So you get the opposite problem if you only drink Gatorade, because Gatorade effectively is salt water. If you're exercising and you're losing lots of sodium and potassium through sweat, you need to replenish it by drinking something like Gatorade, something that has salt in it. But if you only drink Gatorade and you're not losing your electrolytes because you're not exercising, you can throw off your electrolyte balance the other direction, which has the same net result at the end. Which is why if you're stuck on a boat in the middle of the ocean, you can't just drink ocean water. But on the flip side, you can't just drink deionized water either, because that throws off your mineral balance in the other direction. Right? So actually, it's actually not safe to drink deionized water for the same reason. Our cells are used to a certain level of mineral content in our water, and they basically kind of either pump minerals out or pump water in so that they maintain the right balance of electrolytes. If you throw it off too far in either direction, you get the same net result, which is death. Isabel? Yeah, if you're losing a lot of electrolytes because you're throwing up or because you're sweating because you're feverish, it's really good to replenish those. Although it's usually best because you're not actually fully exercising. If you're drinking Gatorade, you want to cut it with water, or just drink Pedialyte, because Pedialyte doesn't taste as good as Gatorade because it has less sugar and less electrolytes in it, but it's actually about the right level for recovering from sickness, which is why we give it to little kids that are sick. And I think you can actually, there's lots of different types of, brands of Pedialyte these days. And a lot of the Gatorades, like, different, not brands, but the different models of Gatorade, I guess you would call it, lines of Gatorade are like, the classic Gatorade is if you're exercising really hard, and then there's like G2 or a Gatorade Ice or whatever that have less in them. Like, it's all just marketing basically, but some of those are a little bit better for you than others. Basically, look at the salt content. Almost all of the electrolytes in stuff like that is in the form of salt. The other definition to go along with electrolytes is, it comes back to the idea of equilibrium that I mentioned earlier. This idea of strong versus weak electrolytes. It actually doesn't mean some electrolytes are better at conducting electricity than others. In chemistry, we use the term strong and weak to talk about whether or not a reaction happens to completion or if it stops halfway or partway. It's never exactly halfway. Basically, some reactions that are called equilibrium reactions will only progress partway to the products before they stop. And they don't really stop. What really winds up happening in an equilibrium reaction, we use a forward arrow and a backward arrow to indicate something is a equilibrium reaction. Basically, when something is in equilibrium reaction, it means that when it gets to equilibrium, the forward reaction is happening the same rate as the backward reaction. And if the forward reaction and the backward reaction are happening at the same rate, think about what happens to your bank account if you spend the same amount of money every month that you make in that month. Your overall bank account looks like nothing's happening, right? If you only look at it from the beginning, at the first of every month. But really, a lot of things can be happening. As long as there's no net change, though, you could say that your bank account is at equilibrium. It's what's called a dynamic equilibrium, which doesn't mean that it changes back and forth. It just means that the net result is zero, even though lots of stuff's happening. So if you have an electrolyte that dissolves in water partly, we can call that a weak electrolyte. So vinegar is a good example of a weak electrolyte, because when you put acetic acid in water, C2H3O2, you have that as a salt, as a ion or a molecular compound, so aqueous. It'll react to make H+ ions floating around and acetates floating around. But only like 5% of the time. Because as soon as you separate these two, they have a tendency to stick back together. So roughly 5% of the time, you have these present as ions, which means it is an electrolyte, but it's not a strong electrolyte. A strong electrolyte would be like sodium chloride. When it dissolves in water, we use just a single arrow to say that it's not at equilibrium. It goes all the way to the products. So sodium chloride is a strong electrolyte because it dissociates 100%. Acetic acid is a weak electrolyte because it dissociates less than that. And so this idea of dynamic equilibrium, we're going to come back to, because it turns out we actually have a way to calculate that. But this is exactly why, back to my point about percent yields at the very beginning, talking about OCHEM and how sometimes 20% is an acceptable yield. Well, if the reaction reaches equilibrium when 20% of your reactants is done, you're never going to get that 100% theoretical yield because the equilibrium stops it from getting there. And it turns out that's a really big concept in OCHEM, in biochem, in water chemistry. We use the idea of equilibrium to purify water. By basically, if you have water that has lead in it, you add an anion that causes the lead to form a precipitation reaction. And so you actually can remove the lead from the system by adding salt to it, because lead chloride precipitates out as a solid. Sodium chloride will dissolve, but lead chloride won't. And then you get a solid that you can just filter out.
Added the wrong amount, then though you'd be drinking that ion.
Right. And this is one of the reasons also that water that's been heavily processed to remove contaminants doesn't taste as good. Why you get hard water, or why you get really soft water out of the faucets in LA, for instance. If anybody's ever tasted the water out of the tap in LA, it tastes awful, especially to us because we have really high standards up here. Our tap water is really tasty. LA's is really bad because they have to remove a lot of contaminants by doing that. And that leaves a lot of other stuff that's not harmful, but it also doesn't taste as good. But if you took it too far, yeah, then you wind up with water that's undrinkably salty. I think they actually use magnesium chloride in a lot of cases because our bodies aren't as good at tasting magnesium ions as they are at sodium ions. But magnesium still doesn't taste good at the levels that they have to add it in certain cities. Any industrial towns, you know, obviously Flint, Michigan would be a place that you would want to use some of that. But really any town that has a history of manufacturing, they have to treat their water really, really heavily to remove a lot of those heavy metal contaminants, which means even if it is safe, and I'm not saying it is in a lot of places, even if it is safe, it's still not good tasting anyway. All right, last concept with 30 seconds left. No, we have a couple minutes, right? Oh shoot, my perspective's off standing over there. I'm not going to make you memorize what dissolves and what doesn't. What we use, instead of having to memorize what ion combinations work and what don't, what are called solubility rules, which is basically just a table. And so usually you're going to have a list of things that are soluble with a couple of exceptions, and a list of things that are insoluble with a couple of exceptions. So basically, if I want to know if a reaction will happen or not, we look at the solubility rules. So we look at what's soluble. Group 1, meaning the first column on the periodic table. Soluble, with one exception. And that one exception is lithium phosphate. This is not exhaustive. There are other exceptions. These are the most common ions that we see reacting together. So if we had sodium nitrate and potassium chloride, if we mix them together, sodium and potassium are both in column 1 on the periodic table, right? That means that sodium and potassium will never form a solid when you dissolve it in water. So basically we can say, okay, well, if you mix sodium nitrate and potassium chloride, we're going to get something where no solid forms. In other words, we just write no reaction. But if we do get a combination, like the second one, sodium chloride with mercury acetate. Well, mercury, if we look at this sodium, we know that sodium acetate is going to be soluble because sodium is soluble, no exceptions. Chlorides are soluble, except silver, lead, copper 1, and mercury 1. So in other words, what this is saying is that mercury chloride is insoluble in water. Chlorides normally dissolve with these exceptions. We have one of those exceptions, so we're gonna form a solid. And so this is a pretty powerful tool because there's a lot of combinations covered just in these 5 lines here. These ones are soluble with some exceptions, these are insoluble with some exceptions. All right, more on that on Friday. Tomorrow, you're gonna boil water.
Yeah.
Thank you.
See you, Mal. See ya. Oh, Michaela, do you have, did you get your test back? Did you want your test back? You don't have to sound so excited.